Okay, and now we're going to look at another hypothesis test that relies on the chi-squared distribution. What we're going to look at is what we call a contingency table. Contingency table is going to look like a two-way table, and our hypotheses are based around independence. Are the two categories independent from each other? So, in this instance, the categories are the grade and the school. So, we're going to look at whether the grade you achieve is independent from the school. So does it matter which school you go to for which grade you achieve? Now, lots of schools would want the grade to be dependent. They would want to say, no, you attending this school gives you a better chance of getting an A grade, rather than it doesn't matter which school you go to, you have the same chance of getting an A grade. So yeah, we're just going to test and see whether or not from this data set there's evidence that the grade achieved and the school attended are independent from each other. There is another phrase that's used here sometimes. We might say there is no association between the grade and the school. That's equivalent to saying the grade and the school are independent. Well, if that's a null hypothesis, the alternate hypothesis is going to be the converse. It's going to say that the school and the grade are not independent, or there is some association between the grade and the school. So once again, as a school, this would be the favourable outcome for H0 to be rejected and H1 to be assumed. Well, particularly when we're talking about top grades. Okay, so let's get down to it. We have our observed values in this table, but we're going to need to try and calculate some expected values. If these categories are indeed independent, then the way that we calculate the expectation is to multiply the probability of respective outcomes. So, if we wanted to find the probability of getting an A grade at school X, since they're independent, we know that the intersection of A and X is going to be the probability of A multiplied by the probability of X. So that's 64 over 120 multiplied by 50 over 120. So that gives me the probability that a student from school X gets an A grade. But how many would I expect? So that probability, we're going to scale it with our total number of trials, with our total number of participants. So we're going to multiply by 120. And I hope you can see here, we've got a lot of instances of 120, and they can actually start to cancel each other out, and we have this easier calculation to deal with. If we were to generalize, we actually have the column total multiplied by the row total divided by the grand total. You can go ahead and do the full calculation if you want, but this will always give you the same expected value, and obviously it's a little bit shorter to deal with. Row total, column total, multiply them, divide by the grand total. Okay, so we're going to use that to calculate our expected frequencies all the way through. So we already know for A and X, it's 18.33. A and Y, we're going to go for 70 times 44 over 120. For B and X, we're going to go for 50 times 24 divided by 120. B and Y, 70 times 24 divided by 120. I hope you can see exactly what's going to happen here for each of them. Finally, for C grades, 50 times 52 divided by 120. And 70 times 52 divided by 120. So this is how we're going to calculate our expected values. Okay, so as usual, we've got expecteds and we've got observeds. We should be able to go ahead and calculate our test statistic. Before we get there, another difference that we're now going to have working with a contingency table is how do we calculate the degrees of freedom? We have the same thinking that we had before of if we know the totals, we don't need all of the values before we can complete the data set. Before we only had one row of values and one total. But now we've got a table, we've got an array, we've got a matrix of values. So we can actually fill in the blanks in multiple directions. These would be the only two values you would need to know to complete the rest of this table. So in a contingency table, to find the degrees of freedom, we're going to do the number of rows minus 1 multiplied by the number of columns minus 1. So in general, for an m by n table, it's going to be m minus 1 multiplied by n minus 1. In this instance, we've got a 2 by 3 table. So, and write this calculation out in brackets, we're going to have 2 minus 1 multiplied by 3 minus 1, and that gives us our answer of 2. Our degrees of freedom for this particular contingency table is 2. Okay, so we have our degrees of freedom, our significance level, our observed and our expected values. We're good to go on the actual hypothesis test. So, as usual, we're going to want to... So I'm just going to summarize all of the important information. Our degrees of freedom, our critical value is going to be 5.991, and I'm going to draw that on a diagram. Anything in this shaded region, any test statistic in this shaded region is going to make us reject H0, and anything not in a shaded region, we do not have enough evidence to reject H0. We're going to calculate the test statistic as usual. We're just going to find the difference between the observed and the expected, square that and divide by the expected. The difference between the observed and the expected, squared and divide by the expected. Some of these we might have been able to do in our heads. Some of them are a little bit trickier. So I'm just happy to type this all into the calculator and get my answer all at once. Observed minus expected squared divided by the expected. Okay, and we follow this all through. In our calculators, we get an answer of 0.916. And that is not significant. So we do not have enough evidence to reject H0. And actually, we have enough evidence to suggest that the school and the grade are actually independent. There was not enough evidence to suggest that the school you go to determines the grade that you get. Okay, so once again, hopefully there's lots of familiar things in the process of this hypothesis test, but we've obviously had a different looking data set. We've had a contingency table instead. Our null hypothesis was different, and for a contingency table, the null hypothesis will always be that the two variables, that the two categories are independent. After we had that independence, we had to look at how to calculate our expecteds. Our expecteds were calculated by the row total times the column total divided by the grand total. And finally, the way that we calculated our degrees of freedom was different. It was the number of rows minus 1 multiplied by the number of columns minus 1. And that gave us our degrees of freedom. So, lots of familiar things in this hypothesis test, a few new things to think about, but I'll leave you now to get on with some practice and see if you can just put this all together.